Hello and welcome to this talk on semi-supervised methods for detecting cyber-physical attacks in industrial control systems. I'm Corwin Stanford from Jackson State University. This was put together for the CSCI 2022 conference, and this research was funded by the U.S. Army Corps of Engineers. Today we're going to be talking about cyber-physical systems and a specific cyber-physical system which we'll get into um, that we'll be analyzing for cyber attacks. We're going to be looking at an overview of intrusion detection for identifying cyber attacks. We'll go over principal component analysis, the mathematics of the model we'll be using, and then we'll talk about how we actually apply it and some techniques for improving that. So cyber physical systems are just any kind of physical system that is controlled or monitored by a computer. Uh, in our case, we're interested in kind of large infrastructure type systems, water systems, treatment, distribution, um, electrical distribution, manufacturing, etc. A lot of them rely on these systems. Often they have collections of network programmable logic controllers or PLCs that, being on a network, are vulnerable to cyber attacks. Many of those systems are connected to the internet or uh, wireless. They're susceptible to these attacks. So two terms that are worth noting here: industrial control systems. This is just the collection of electronic control systems and associated instrumentation used for these cyber physical systems or industrial process control. And then supervisory control and data acquisition, or SCADA systems. Uh, this is a subset of ICS, but this mainly focuses on the graphical user interface and the supervisory aspect of these industrial control systems. But these terms get used a lot, so it's worth pointing them out and defining them here. Okay, the system we're going to be looking at is the hardware in the loop based augmented industrial control system, or the HAI dataset, and there is their link. You can find the datasets there, as well as some information on how it's put together. This is a lab scale ICS test bed, uh, so it is small. It's not industrial size. It's small enough to fit in a lab, 1 or 2 rooms. Uh, the hardware is combined with a simulated hardware on a computer, um, where there's feedback and interplay between those two. In this case, it's a hydropower generation system, both steam turbine and pumped storage hydropower generation. This particular dataset is the 2103 dataset from March of 2021. Important facts here are that it's collected once per second, so each row of our database is 1 second of data. There are two individual data sets here. One contains normal operating data, 60 hours of that, or 216,000 data points. The other data set, the attack data set, is 12 hours long. It contains 5 attacks in interspersed with this normal data. So there are 43,200 data points in this second data set. Only 629 of those are attacks. So those are split into 5 groups of individual attack events. Finally, there are 78 features along with a date time feature and a label feature. We don't concern ourselves with a label feature because we're looking at unsupervised and semi-supervised methods, not supervised methods that would take into account the label. We do use the label afterwards to assess the effectiveness of the model, but in building the model, the label is not used. Okay, so an overview of the data types in this model, or excuse me, in this data set. We have 4 example features. We have the first one, which is highly oscillatory. We have a second data set, which is like a steady state or step function type that uh, maintains a steady state for an extended period of time before jumping to another state. We have a similar feature, right below that, where we have a number of relatively uh, consistent values, but it oscillates between these very quickly. So we're jumping from one to the next uh, rapidly enough that these look like essentially straight lines. And it is worth noting that these have very low variation. We go from 12 to 12.04. So this could just be a highly sensitive sensor recording data that is not really fluctuating very much. And finally, we have some periodic data. When there are a few examples of each of these in this data set of these 78. We've just chosen 4 to kind of point out the variety we have here. Okay, so on to intrusion detection methods. So the typical method you see in most malware prevention software is a signature-based intrusion detection where we look at the live data, log data coming in, and we compare that to some existing known attack patterns. So you get your attack patterns are updated frequently. Uh, you download new security updates, and that's what these are containing, these attack patterns, so you can compare your traffic to that. Anomaly-based intrusion detection, on the other hand, doesn't have any signature to compare it to. The two methods we have here are unsupervised methods. And these are typically clustering type methods where we just look at the data and look for statistical outliers in that data. In the case of PCA, which we'll be doing today, this is semi-supervised, meaning that we're training this uh, on normal activity. So we're learning what normal activity looks like. So we use some machine learning method or statistical method to establish a baseline pattern of trustworthy activity, and then we look for things that don't fit that baseline. So we compare any new activity to that and see whether it fits the pattern or is an anomaly. So the advantages and disadvantages of each. Signature based is very reliable as long as something is a known attack. However, it can't detect novel attacks. Anomaly based intrusion detection systems, on the other hand, can detect novel attacks. However, they may not be as reliable for signature based attacks. Well, most of the time, they're not going to be as reliable um, in that event. And of course, these also can classify benign behavior as malicious. So you can have a false alarm. Although to be fair, you can also have false alarms with signature-based anomaly detection methods. Intrusion detection, excuse me. Okay, principal component analysis is the mathematical technique we'll be using here. As I've said, this is usually, I think I said this, it's often used for dimension reduction of the data set. So I'll kind of give you an overview of how that's done and then how we're going to do it. Don't worry, it's not nearly as bad as it seems. This is pretty straightforward method. We only have a few formulas we need to look at here. So what's done is we calculate the covariance matrix for the data set. And this is our normal trusted data. So the way we do this is we'll just an example for two features A and B of the data set, or two columns of your data A and B. You can calculate the covariance between those two columns by taking each value, subtracting or each individual data point for that feature, subtracting it subtracting the average value from that point, and multiplying it by that same variance for the other feature. So we do that for each data point AI and BI of our two features, multiply those together, divide by the total number of elements or events. That tells us how these things vary together, or how they covary. Now we just need to do that for every possible combination of features in the data set. So just to give you an example here, if we have, this is a three feature example, if we have features X, Y, and Z, we can calculate the covariance of every combination of those. We can do covariance of X and X, X and Y, X and Z, Y and X, Y and Y, Y and Z, Z and X, Z and Y, Z and Z. So every possible combination, and some of them are repeated. For example, covariance of X and Y is the same as the covariance of Y and X. Right? This is a commutative operation, multiplication here. So we have a symmetric matrix here. The top right is the same as the bottom left. So that saves some time in calculating this thing. So what do we do once we have our covariance matrix? We find the eigenvalues and eigenvectors of that matrix. and we're going to be looking at the explained variance of each of those eigenvalues and its associated eigenvectors. So doing that is also a very simple calculation. We order the eigenvalues from largest to smallest. We calculate the explained variance of each. We just take its value and divide it by the sum of the eigenvalues. And that tells us how much of the variation within the data is explained by this eigenvalue. Um, so I've graphed that. I've graphed a cumulative explained variance. So for each one, we add the variance of the one before it. So we see, like, for example, here, the first three eigenvalues explain almost 50% of the variation in the data. By the time we get to 30 eigenvalues, we've explained approximately 100% of the data. So normally for PCA, we would take these earlier values, the ones that explain the majority of the information, we would keep those and throw out the rest. We would use these first ones to transform our data set to a lower dimension, a 30 dimension space rather than a 78 dimension space. In our case, we want these ones that exhibit very little variation in um, normal operation. These are the ones we're going to be using because during an anomalous event, these will show that fluctuation. So that's it. That's the math we have to go over. Um, Now let's look at some examples of this for the HAI data set. Here we have PCA component 1. We've used that to transform um, our, our features. So this one has high variation during normal operation, whereas the component 40, which is further down that list, it's further to the right, has very little variation during normal operation. Now, what is that? We're going to look at this component 40 again. Here's component 40 again during normal operation. I zoomed in just a little bit to show what happens during an attack. During an attack, and that's these purple bars here, you see we've got lots of, we see our feature, our component here spikes. Same here, it kind of spikes down. We've got a threshold here set at 4 standard deviations. That's where we've set our anomaly threshold. Anything beyond 4 standard deviations, we consider an anomaly. And you see this does a pretty good job of capturing both of these attacks, although there are some false positives as well. Looking at the results from this, of the 600 or so attacks and 620 in this data set, we captured 482, although we also captured 1,200 false positives. The other metrics here, and I've got their definitions. You can pause and look at those if you'd like. Accuracy, 97%, seems very high, but it's not unusual to have high accuracy with these various machine learning methods. Precision is fairly low, as is the F1 score. So definitely something that we can improve upon. So how to improve upon this? So the PCA components are not perfectly consistent with how well they do at detecting these anomalies. So we just taking the last 30 through 78 may not be the best idea. If instead we use these to transform the benign or normal operation data and then reorder these PCA components based on how many anomalies we get from the normal data, uh, we can just select the components that don't give us a lot of false flags, right? So we order these from the the fewest anomalies they detect in the normal operation data to the most they detect in the normal operating data. And we're just going to take the ones earlier on in the list. So what does that look like? So here I've got that ordering. I've reordered these by how many uh, anomalies they detect during normal operation. Uh, that's the order we've got from 0 to 48 here. And then I've applied these to the second data set, the one that contains attacks. And as predicted, the number of true positives increases relatively smoothly. As false negatives, it's just the correlation of that, or the inverse correlation, so it is the opposite. False positives, on the other hand, stays relatively flat until the end where it jumps up. So this is ideal. This is what we'd hope for. We can just disregard the last few of these. In our case, I think we disregard the last 25%. We get better results. So when we use this shortened list of components, uh, our true positive goes from 482 to 447. So we do lose a few of these attacks or attack events. However, false positives drop 90% from 1200 to 110. So that's a great result to see to make this more useful of a technique. And all our various metrics seem to support this. Accuracy's gone up more. False positive rate has dropped. True positive rate was also unfortunately dropped uh, a small amount. Precision increased drastically. F1 score increased drastically. Recall did drop a little bit again because we've lost a little under 40 of these seconds of attack. Okay, the next method we're going to talk about here is using a variable threshold. So instead of a constant threshold, we look at just the immediately preceding data at a particular point and use that to establish a threshold of acceptable future behavior. So yeah, this is I believe this is again 4 standard deviations using 3% window of preceding data. Um, so there are some pros and cons. So this is a normal operating data, this big spike here. Normally this would be flagged. This would have been a false flag or a false positive. You see using variable thresholds, none of these are flagged. Uh, of course, on the converse of that, this spike over here would have been considered anomalous using a constant threshold. It is not considered anomalous here. It's not outside of that threshold. However, on the same note here, this attack is still captured fairly well using this method. Before we look at the results of this, we're going to go ahead and do the same reordering we've done before. If we reorder these components and we look at what happens, um, we have a very similar effect. True positives increase uh, relatively consistently. Uh, False negatives decrease at the same rate. The difference here is our false positive rate. It's constantly climbing throughout this, whereas before it was flat. So that's an unfortunate result, and it's not clear exactly where this cutoff should be in selecting these components. Uh, Here we select roughly the first 25%, and I've graphed all of our performance metrics here to see uh, why we chose that method. That's where our recall is increasing still, but it's done. The majority of it's increasing. F1 score has increased to its peak before dropping, and precision is at its highest value before a steep drop. So that's when we chose this particular value. There's no great answer as to why we chose this. Looking at the false positive rate, you see this is also right before the false positives start to get into the 200 range. So it could be a better choice here, but that's the reasoning for this choice of 25% cutoff. And now we can look at the results of these final methods. Um, so again, I'll just glance at the true positive rates. So the variable threshold in general, we've decreased a little bit more in our true positive number. False positives are lower than they were um, with our initial method, but not as good as they were with just a shortened list and a constant threshold. Variable and shortened, so this is the last method where we ordered it and used a variable threshold. We had the best result here, the lowest number of false positives. We also had the lowest number of true positives. And again, you got all the various performance metrics there. Just a repeat of this chart where I've highlighted the winners for each column or for each row. Uh, you see there is a tied accuracy between our shortened list and our variable and shortened. So this first one was constant threshold. This is variable threshold with a shortened list. Those are both tied at 99% accuracy. Not that accuracy is the best metric here. And there's our list of conclusions. essentially everything we've seen here before. There are drawbacks and benefits for each of these methods that need to be weighed for the application. And there are our references. And if you've made it to the end, I appreciate it. Thank you for coming to this talk on semi-supervised methods.